Let's look at a different scenario in which we want to optimize. For every scenario you see, you're going to realize you're going to need a different differentiable function. In this particular case, we're looking at a graph in the Cartesian plane. What are the points on the ellipse that are farthest away from the point 1, 0? And the equation of the ellipse is given here. Remember that we could write our information in terms of two categories. I typically start with the constraints. And the constraints are basically any restrictions on your variables that you're planning to use. In many cases, the domain is going to be related to constraints. But in this case, we don't even have a function. We have a curve in the Cartesian plane. But what we can do is draw this curve, especially if you know its standard form. Its standard form is going to look like this, just algebra. And once you have the ellipse in standard form, you have the opportunity to draw this. Remember, the a here is just 1, so it's only 1 unit to the right. And that will give us the minor axis of the ellipse. The major axis is referenced with this 2 unit here underneath the y. We already know this ellipse is centered at the origin. And so it's an elongated oval that is stretched over the y-axis. And we want to know what are the points on the ellipse that are farthest away from this ordered pair right here. And just by eyeballing this, you think the ordered pair would be somewhere in quadrant 2, and there will be another ordered pair somewhere in quadrant 3. Now I'm going to try to figure out what the objective is. The objective is to maximize the distance d. Okay, we're trying to maximize the distance d. And your first thought is probably the distance formula. So if you write the distance formula, the distance between 2 points, hypothetically, I could label this a point on the ellipse, x comma y, and the distance between the 2 points would be x minus 1 quantity squared plus y minus 0 quantity squared, and that is the distance between 2 points, where xy is an arbitrary ordered pair on the ellipse. Now the issue with this is that if you try to maximize this square root function, it will yield more than one critical number, and it could actually make things quite troublesome. So instead of looking at this, we're going to define a different function. We're going to consider capital D. We're going to consider capital D, and capital D is going to be this function here. It's simply going to be the square of the equation above. So I'm going to have x minus 1 quantity squared plus y squared. And this is actually called the square of the distance. So instead of trying to maximize the actual distance, we're going to try to maximize the square of the distance. And this is going to be much more useful. Now the issue with this capital D equation is that there's more than one variable. There's actually 2. There's an x and there's a y. So it'd be nice to be able to solve for, it would be nice to look under the constraints and see if I could make a substitution so that I could get d in terms of one variable. And the answer is yes, this is going to be very much possible. Notice if you realize you have 4x squared plus y squared is equal to 4. And so y squared is going to be that. That is y squared. I'm going to take that and put it over here. And now we have d as a function of x. And we could actually differentiate this function. Why don't we differentiate this function and start looking for critical numbers? And we're ready to find our type 1 critical numbers. Notice we do not have any type 2 critical numbers this time. So we get C to be negative 1/3. What we're going to do with this critical number, we'll put this on an x number line and we'll test the first derivative. Now what's a good first derivative function? This one would be really, really good. I'm going to box this one here or circle it. Now, really not sure what x values could be over here, so I'm going to just let this be an arrow. It really doesn't matter too much because we have one critical number. Now, I'm going to test this in the first derivative. Let's test negative 1 in the first derivative and see what we get. We get positive. And then let's test 0 in our first derivative and see what we get. We get negative. So that means the square of the distance function is increasing, and then the square of the distance function is decreasing after the critical number. That means we have an absolute max. This is so awesome. So at c equals negative 1/3, the distance away from 1, 0 is an absolute max. Or absolute maximum. That is what we want. Now, how do we get the actual points? So I'm going to take this and I got to go back . No problem. Let's solve for y. And when we take the square root of both sides here, you do have to be careful because this is now the absolute value of y. And there you go.